Welcome to Robotics in Depth. Today I'm honored to have Lael Odhner here, and we're going to talk about his robotic hand, which I think is a very interesting mix of soft and stiff. And he's going to describe it to us. Welcome to the show.
Thank you. This product that we have been working on for a while is what we have been calling a compliant adaptive gripper. And the idea is that the fingers of the hand not only can be moved by a motor that pulls them in and out, but it also has a range of floppy, compliant motion. Now, I want you to try a little experiment. I want you to take out your hand, and I want you to twist your thumb. You notice that you can actually rock your thumb back and forth a little bit. Now take away your other hand and try to do that again.
You can't.
You can't.
No.
But it's pretty clear that one of the things that makes our own hand work very well is that it actually has the ability to conform very closely to the surface of anything that you're trying to grasp. And some of that is active, controlled thing you do, and some of it is something that actually is just a function of the passive mechanics of the system. And that's the entire idea behind our robot hands. We started RightHand Robotics to commercialize these hands that we had been building for DARPA. DARPA had a competition called Autonomous Robotic Manipulation, and they commissioned 3 robot hand designs to try to improve the dexterity and cost of lightweight robot hands. So it's entirely self-contained. It's very lightweight. It only weighs 800 grams. And it has 4 basic motions. So each of the fingers can move independently with just a single tendon. And then it has a 4th degree of freedom where it can use to actually pivot the fingers around like this. But where we think this is really interesting is that this hand was designed not for the kind of precision industrial gripping that you usually see in automotive applications or something like that. This hand was designed to grasp everyday objects. So when you go to flip on a light switch or pick up a cup off the table, you don't sit there and image it and know to within a millimeter where it is. Sometimes you reach over, you just wait till you make contact and then close your hand. And these fingers are designed to operate in a very similar fashion. You know, you want to be able to conform to unknown surface geometry. You want to be able to deform if you accidentally hit a wall or a table or something immovable. You don't want to break your fingers.
Or whatever you hit, for that matter.
Or whatever you hit. You know, you can if you're trying to pick up a piece of fruit, you don't want to make orange juice or something, squeezing it too hard. And so the idea with this hand was that it does just that. It's extremely floppy until you close all the way around an object, and when you have a firm grasp, it's actually much stiffer, because what happens is the object itself in the middle of the grasp provides the rigidity that you need to fully control the object's position as you then move it around afterwards.
Yeah, that's really cool that the hand, and I guess you showed that with the thumb, the hand and the object works together to actually grip it.
Yes.
Yeah, instead of trying to force the hand to do all the work.
Yes, and originally in the robotics research literature, people had believed that in order to have dexterous hand behavior, you had to have actually more actuators than the object had degrees of available motion, because you needed to be able to exert a controlled force in any direction on the object. And that is still notionally true if you want to have complete and arbitrary control. But what we found is that most people want to do much simpler things. If you just want to pinch something, or if you just want to hold it and maybe roll it back and forth between your fingers, sort of go, like turning a radio knob. That actually requires many fewer motors than a scientifically correct hand would.
But there's a lot of space that can be addressed by this Lester actuator.
Oh, absolutely. We think that a hand such as this, with only 4 motors, can probably handle most of the objects of everyday living that you would encounter. So you should be able to pick up anything you see in your kitchen with this hand and move it around. You may not be able to play a piano sonata, but how many times a day does one do that?
Oh, at breakfast I always do that.
Yeah. So when we are working on this, we were thinking very carefully about things like assistive robotics. You know, where you want to put a hand on a robot that has to navigate inside a human household. We were also thinking of things like disaster relief or bomb disposal. And again, those are situations where what you want is a robot that can actually navigate human environments. You know, if there's a suspicious gym bag that you want to be able to open up and search through to make sure everything is safe, you're dealing with zippers, you're dealing with snaps, you're dealing with objects inside the bag, and all of those things are objects of everyday living. They're not precision machined pieces to pick up very carefully from here and put them over there. So in sacrificing that precision, you gain a huge range of versatility, which is really what we're after.
And I think that reducing the from the scientific to the practical, you also reduce the complexity and therefore the price, and making it available to people.
Oh, absolutely.
A hand you have is better than a hand you don't.
Absolutely. And one of the core things we hope to address with this, after working on this DARPA project, we have seen many people design beautiful pieces of robotic hardware for researchers, and they will make only one copy. And they will take a lot of videos of it, and they'll publish a lot on it, and they'll tell everyone, look what we had. And everyone says, well, that's great, but can I get one? Can I use one? So we specifically decided that the first product our new company would release is this. This is the RightHand Robotics Reflex, and it's available to researchers specifically so that the next generation of us, the people who sat there in a lab and said, well, gee, I really want a better robot hand, they don't have to go back and re-implement. They can actually just go and buy it for a fairly affordable price, and they can even take it apart and modify it. It's designed to be very modular, very simple, and also very robust, so that it's very hard to break. And in the unlikely event that you manage to break it, replacing any one of the pieces is not very difficult.
This is really interesting. So this is now available to researchers.
That's actually for a couple of reasons. Most prominently, I think, that as a young company, we have found that things like insurance and liability, but also managing expectations is very important. You know, this is a very new product. It was really designed for use in a research environment, and we're hoping that we can start there and we can see what people want to do with it, and they can see where it succeeds and fails. It's a very good way for us to try and get people's mental gears turning without having to deal with the extreme difficulties that companies often face with things like commercial support. So as a when you're doing something bold and somewhat uncommon, it's very good to start with the research market.
Yeah, because it also allows you to iterate once more on the design and iron out those hard to find bugs and issues.
Absolutely, and researchers are great for that because you know, you buy a robot and you give it to an untrained incoming student. You say, hey, write a program that uses this thing, and most of the time someone will start it up and they'll put in a plus sign instead of a minus sign, and it'll go into the table.
Yeah.
And you know, what do you do with that if your hand cost $50,000? That gets very expensive to do.
Yeah.
But for us, having designed this, it's a wonderful stress test.
What were the main challenges? You set out to do this hand with some form of a basic idea and then explore the space. Can you talk about the start of this?
Oh, sure. Our basic philosophy in designing these hands was to start by saying, what really do you need to do to an object in order to manipulate it? If you're just talking about picking up an object and putting it on the end of a robot arm and moving it around, so if I take this hand and I move it around like this, do I really need a complete firm grasp on it? So could I, for example, Could I pick it up and move it around as it were on a fishing line or inside a net or something like that? Well, you could. And that won't be useful for everything you want to do when you manipulate. But it's a good place to start because it implies in some ways the simplest of mechanisms that you could use to grasp something.
And that is a huge space in its own right?
Absolutely. And so when you start there and say, okay, well, if I want it to be a little firmer than that, I do need to actually, say, encircle an object and make sure that I can get my fingers around it. That adds a few more constraints on how complicated the mechanism can be. So when this project first started, the student on it, Aaron Dollar, began with a design that used only a single motor, connected with a differential to 4 fingers. And the idea was to say, well, if all you had was one motor, how well could you grasp and hold objects? And it turns out you can do very well. When we wanted to do a little more, we went to a slightly more complex design. But by starting from 0 and moving upwards, we have a huge advantage in cost and complexity over someone who tried to start at a fully articulated hand and then cut degrees of freedom downward, because that way is much more difficult to go with. You end up having to think much harder about where your redundancies lie, whereas here in the constructive approach, you start from nothing and then just add functions as you need them.
Very interesting. So what was the main challenge? You had this first, the one motor thing, then you moved on to this. Is this then a 3 motor thing with 3 fingers, sorry?
So it's a 4 motor thing. Because,
yeah.
like I said, you can move these back and forth, and that's very important because if you think about the things you need to do every day, you often need to grab cylindrical things. So you put something right through. Sometimes you want to grab spherical things, so you can go like that and come in like that and get a 3-fingered pinch on them. And then sometimes you want to pick things up just with an opposed pair. And that's what this motion is really good for, is you can pick something up with 2 fingers and you can actually even manipulate it a little bit with a third while you have it in that position.
Is there a reason to it having 3 fingers and not 4 or 5 or... I guess 2 fingers would seriously limit you with the spare, but why
3 fingers is the smallest number that you could use and still constrain something in 3 dimensions and manipulate it in 3 dimensions. So that's, when you talk about this tripod grasp, think like a 3-legged stool. A 2-legged stool wouldn't be much use to anyone.
No, but a 3-legged one is nearly comparable to a 4-legged one.
Exactly. And we found that the added cost of putting a 4th finger on just didn't pay off relative to the 3-fingered version.
Is there a difference between the 3 and the 4 that would be interesting to just know? Was there something that you can do with the 4 that you can't do with the 3?
I don't think we found anything we could do with the 4 and couldn't do with the 3. I think if
that is in its own right very interesting.
Yeah, it's also an artifact somewhat of our design. If we were trying to make something that was more highly articulated, if you were trying to do what people call finger gating, where you remove one finger and try to sort of walk an object around in your hand, then I think 4 fingers would be much more valuable than 3. But we really didn't attempt to build that kind of functionality into this hand.
Because it's also, if you look at how we grasp things and how we interact with our environment with hands, doing that is a niche thing, right?
Yeah.
Most of the time we interact pretty simply with what we interact with.
Absolutely. And many of the robots that people are using for machine tending and things like that, you don't even have a hand, you just have hook. So if you want to pick up a part out of a machine, if the part has any kind of loop in it or hole in it, you can just stick a hook in and pick it up like that. So when that's your competition, you keep it as simple as possible.
Yeah, also to keep the price down.
Yes.
And make it available to people. Again, the hand you have is better than the hand you don't have. So
oh, absolutely.
Irrespective of the different qualities of the hand. So how do you see this going forward you just launched the company. The company is how old?
The company is 1 year old.
1 year old, so.
Yes.
And where do you see the road ahead for you and this product?
Well, our big thinking is that we think we have developed a gripper technology that can vastly expand the range of things one can grasp. And that's not one direction ahead. Unfortunately, that's thousands of directions ahead. And so we are largely in the process of sorting out exactly which one of those 1,000 applications is really the best fit and where's there the most need. Because many companies that make grippers already do an excellent job in addressing existing needs. What you don't see, what you never see, is the people who don't even think about using a robot to grasp and manipulate something because no one's ever shown them that it's possible.
Or that it's ridiculously expensive.
Yeah. And so it's to some degree an exercise in blue sky creativity to just look at a lot of different applications and say, hey, could we grasp that? We went around to a farmer's market and a bookstore and a bunch of places, and we just took the hand, and we got some very strange looks from people just walking in, pointing the hand at something and trying to pick it up. And what we found is, the possibilities are nearly endless. It's really just a matter of finding something where the customer fit is right.
Yeah. You need to go to a hardware store and an IKEA and all of these places.
Yeah,
but it's really good that it's portable and that you can have it out there, and the price point being interesting is also great. So this was really interesting to hear about how we can start to actually manipulate the world in this detail, because I think we see a lot of robotic arms and we see mobile platforms. There's much less choice in what we put at the end of that arm than the amount of arms we see.
Oh, absolutely.
And that's because it's complicated.
Yeah.
But it's also so that if you have a mobile platform and you have an arm but no hand, you don't have a product, right?
Yeah.
You have to do something with this. And
one thing I would say though is it's coming.
Yeah.
I've talked to half a dozen people who are starting companies with their own designs for grippers.
Yeah.
So I think that when we see mobile platforms coming and arms coming, you're seeing a steady progression. You're seeing a lot of people making lower cost cameras. You're seeing a lot of people making lower cost inertial navigation systems and drones. And I think that the hands are just one more step down the road.
Yeah.
And in not too long, we will be swamped with people coming up with new hand designs, and I think that'll be a great thing.
Yeah, and I'm sure you're going to be one of the successful ones doing that. Thank you very much. It was so nice to speak to you.
Well, thank you.
I hope you liked this episode of Robots in Depth. I'm proud to produce Robots in Depth with the support of the sponsors, Carbon Robotics and Aptomica. Carbon Robotics is redefining the relationship between humans and machines by making advanced automation dramatically more accessible, with low-cost robotic arms, integrated vision, and a powerful task intelligence engine that automates tasks no human was born to do. Carbon Robotics is proud to support Robots in Depth in their goal to elevate the global robotics ecosystem. Aptomica rents anything in modular robotics. Dream, rent, build. Visit aptomica.com to connect. If you like this episode, tell your friends, give us a thumbs up, subscribe and turn on your notifications. I am Per Sherboy, and I'll see you next week in another episode of Robots in Depth.